Man, I just got this piece of uranium glass. I wonder how many microsieverts per hour it puts out. Oh wait, that's right. That antiprotons guy, what is that guy? Tom at antiprotons.com? Antiproton? Whatever his name is, he said you can't use microsieverts per hour or milliroentgens or MREMs because they require that you know how much energy is being put off by this and a few other random things. Well, that's okay for that, but what if I do know how much energy is putting off? What if I know what's in this and how much it is and how much it puts off? Why can't I figure it out then? Hey folks, this is Tom from anti-proton.com. You're absolutely right. If you have a Geiger counter, like this Geiger counter here, for example, and you're detecting some random thing that's producing radiation, whatever that could be, and you don't know what the energy is, you can't use microsieverts per hour or milliroentgens. But if you do know what the energy is, you can. You can even calibrate your Geiger counter so that you don't have to do the math in your head and you can just hold it over and know. Let me show you how. Now, the problem I have is that I don't keep a lot of very strong, powerful sources around me. For one of the reasons I don't wish to be exposed to that much radiation. Calculating something like this is depression glass, is very difficult. The reason is it contains natural uranium. If you've ever looked up the natural uranium decay series, meaning the things that come from natural uranium over time and decay, there's a long list. And each one of them produces a different type of radiation. Well, not every single one is different, but each one of them produces a collection of alpha, beta, or gamma, and sometimes a mixture of them, of different energies. It would be quite difficult, but not impossible. Knowing that this is natural uranium, calculating the activity of it, you could actually figure it out. Let me show you something a little bit simpler. Let's use polonium-210. Polonium-210 is something I do have a source disk for, and I can show you. As soon as I get a strontium-90 or cesium-137 source disk, I'll show you how to do it with that as well. Alpha is a little tricky, and there's a couple reasons why, and I'll explain in a minute. And polonium-210 produces alpha radiation. It doesn't produce, well, it actually does produce a tiny drop of gamma, but it's almost inconsequential. But anyway, it's a little bit harder to do. The problem is with things like light salt here, there's just not enough radioactivity in them to calculate it easily, although you still can. When you have something like potassium chloride, polonium-210, something where you know what it is, then yes, of course you can calculate exactly how much energy. And once you do energy, then you can know this. One sievert, I sometimes misspell I before E, E before I, so if I misspell it, don't shoot me, is equal to 1 gray times the weighting factor for the type of radiation and also the weighting factor for what it's zapping. The person, the arm, the leg, what part of your body. To put it simply, for the whole body human, usually you use a 1. You'd use fractional amounts for hands and arms. Like your finger here can tolerate tremendously more radiation than your body here. So this might be a tiny little number like 0.01 or something. So you take the amount of radiation you have and multiply by that and come up with a much lower damaging effect. The types of radiation weights, well, there are alpha, beta, and gamma. This one, alpha, is a 20. It does 20 times more damage to you than the others, which are 1 and 1. This is not to be confused with a column vector, by the way, if you are thinking that. This is just me showing you that it could be this, this, or this. And then a gray. A gray is a unit of absorbed dose. What this means, and I'll tell you what a gray is in just a minute. If you have an object and you have a source of radiation, as it emits radiation, the radiation that is deposited in a particular period of time in this unit, this object right here, is called its absorbed dose. That's how much energy it absorbed. Now, the sievert seeks to take this and figure out what the equivalent dose is, meaning what's the real damage. Alright? If somebody shot you with a 22 caliber bullet and a 45 caliber bullet, they're both an absorbed dose of one bullet, but the equivalent dose would be tremendously greater with that 45 because it does more damage. Kind of a bad analogy, but you get the idea. Okay, 1 gray is equal to 1 joule of energy divided by 1 kilogram. Let's draw that a little better. 1 joule, 1 kilogram of mass. So, if this object produced radiation that amounted in one period of time, whatever amount of time we're looking at, to 1 joule, and this object here was 1 kilogram in size, then this would have accepted 1 gray of radiation. Let's say we're looking at grays per second, then let's say that this puts out 1 gray of radiation every second. 1 joule of radiation every second, and this is 1 kilogram, then this is accepting 1 gray per second. Do you see what I mean? And if it turned out that this were a person, it would still be 1 gray. But if it turned out that it was a person in alpha radiation, it would be 20 times that. It would be 20 grays. Well, in this case, 20 sieverts, actually. So, grays times this little coefficient guy right here, which tells you how deadly the radiation is. Neutrons and things have their own as well. I'm just not putting them up. And this little guy here, which tells you what part of the body is hitting, which is going to be a 1 for a full body, equals a sievert. Alright? Hopefully that's not too complicated. Rads and REMs have their own equivalent scales. A rad is an absorbed dose, whereas a REM is an equivalent dose. Röntgen equivalent man. That's what it stands for. Okay, so let's take this plus polonium and figure out Microsieverts power, and then let's calibrate the Geiger counter so we can use it for that. The very first thing we'll need to do is find out how many counts per minute we get from our polonium. So, here we go. When working with something like polonium, it is important to always be very careful. Polonium is very dangerous. In fact, it is incredibly dangerous. It is 250,000 times more deadly than arsenic. Always take a piece of paper and put it down. Work on the polonium on the piece of paper. The probability of a piece of polonium breaking off from my sealed source, well, the polonium is not actually sealed. It is exposed, but it is a polonium chloride bond to silver. The probability of it breaking off is very, very small. Any pieces of it coming off, incredibly, ridiculously small, but not inexistent. Alright, now let's carefully extract the polonium. Here it is. Realistically speaking, I am probably being a bit over precautious, but it is a dangerous little thing. Here it is. Let's flip it upside down and let's test it. As you can see, we get nothing with the cap. Once we pull the cap off, plenty of radiation. Okay, now it is not necessary for us to detect the counts per minute off of this polonium-210. But for a side project, it would be interesting to get an idea of how efficient my Geiger counter is at detecting it. There should be approximately 3,700 becquerels coming off of this. 3,700 decays per second. I wonder how many I will actually detect. What I will do is set my Geiger counter at a distance of 1 centimeter from the target, and then I will detect several minutes worth of counts and see what happens. This is a side project to calibrating the Geiger counter. I'll show you how to do that correctly in just a minute as well. But first, we will do this as a bit of a side project. In order to calculate this correctly, the Geiger counter must be approximately 1 centimeter from the target. It's not that it has to be 1 centimeter, but it just makes it easier for my math, and I'll use this measuring device here for figuring that out. The polonium sample itself has a little bit of depth inside. It's not touching directly the plastic, nor do I want it to touch the plastic directly. What I will do to ensure that this is exactly 1 centimeter from its target is I will take 2 pencils. I'm aware this is a little bit unscientific, but I don't have a rig for holding this together tightly. There. Now, let's make sure that you can see this in the video. We will fold the paper underneath. There. We will place the pencils in place right here. We will put the Geiger counter, oops, let's cut the sound off, it's sort of loud. Put the Geiger counter right here on top. Place the plastic cap underneath the Geiger counter to hold it in place. Now let us test and see for a fact whether or not this is actually 1 centimeter's distance. Alright, now we use the measuring device. Yes, we are 1 centimeter's distance. 1 centimeter's distance, almost exactly, and you'll see in a minute why that's very important. At 1 centimeter's distance, our Geiger counter squeals. At 18,000 counts per minute. If we were to believe the microsieverts per hour, we would believe 5.1, 5.3 even. But that's not correct, and we'll see in a minute what it really is. Alright, let's set our timer. Our timer is for 4 minutes. Let's make it 5. No, let's make it accurate. Let's make it 10. And then let's start it. Look at that go. 500, 1,000 counts, 1,400, 1,700, 1,900. My God, this thing detects a lot of radiation. Alrighty. We can only hope that in 10 minutes it doesn't exceed its own ability to calculate. Alright, so we pull off our glove, put that aside, and now let's get to the math. Alright, let us now calculate how many microsieverts per hour I should be getting from that polonium sample. I've written it all up here in details. It's several, well, it's actually, the original calculations are several pages, and I did them all last night. Oh my God. So anyway, you probably can't read that anyway, because I flashed it too fast. But let me write it up on the board, and let me do it in a way that's a little bit easier to do. I warn you, you have to do a little tiny bit of math for this. You have to do it. If you don't want to do math, go away. But nothing weird. We're not going to do any strange calculus or anything like that. Alright. Polonium 210 calibration. The activity of that disk is 3,700 decays per second. 3,700 becquerels. This is the Geiger counter. Here's the check source. It has a little dip in it. and right down here is the material. Only rays that are going nearly straight are able to make it out. Ones that go at an angle, stop. Ones that go down, stop. That means that this little thing here sort of rectifies it and makes a little beam out of it. Beam. Okay. We can probably roughly assume, this is an assumption, but since this polonium is in a very tiny amount and it is mixed with chlorine and bonded to silver, that it's nearly flat. I mean, it's not one-dimensional or two-dimensional or whatever, but it's nearly flat. Let us assume that 50% of this polonium is getting up into the tube. Alright? We're just going to, assume. So that's an important thing to take into account. Now, this right here is sort of an important thing to take into account too, the distance. The reason I did the distance calculation is because as alpha particles move through the air, they get caught up by the air. They're very strongly positive. They attract electrons and become helium. Alright, if you were doing this for uranium, like that piece of uranium glass I had earlier, this wouldn't matter as much. Well, it would, but not as much. And if I had like a straight beta emitter, or even better, a gamma emitter, don't even worry about it. If you were going to calculate a couple feet or something, it would make a difference. Technically, it does make a little difference, but when you're just doing a regular calibration, which is already going to be off by 5 to 10% anyway, it's not a big deal. But when you're dealing with alpha, well, let me explain. Where's my meter stick? 3.97, I think it is. Let's see here. I have it written down. I did a lot of math last night. It was pretty creepy. 3.97 centimeters. How far is 3.97 centimeters? I'll show you how far it is. That's the start of 1 centimeter. 3.97 is nearly 4, and that's it. This right here represents the total distance in regular temperature air, room temperature that I have right now, at this altitude and pressure. This is how far the alpha particles can go from my Geiger counter. I can take my Geiger counter and show you that this is true. I calculated this mathematically. It goes beyond the scope of what we're doing here because most people aren't going to be calibrating for an alpha source, and this is something you mostly are going to have to do for an alpha source. So I'll just show you for giggles, but don't worry about this being part of the calibration. What did I do here? This is some nasty stuff. I took the continuous slowing down approximation for an alpha particle, and the alpha particle was, let's see, I've got it right down here, 5.307 million electron volts, and that equaled 10204 times 10 to the negative third grams per centimeter to the third power over air, which is 4.78. It's like the density of air times 10 to the negative 3 grams per centimeter squared, which equaled 3.97 centimeters. I'm reading what I did yesterday on a piece of paper. Yeah, I did all this crazy math. Don't worry about it. But what I'm trying to show you, and this is just for anybody who does know how this stuff works, and they're like, how did you figure that out? What I figured out from this was that when you have an alpha particle, all right, and it's going from 0 centimeters, 1, 2, 3, 4, 5. 5, 4, 3, 2, 1. When it's moving across centimeters of distance, and it has particular energy levels, millions of electron volts, it works like this. There's this little curve. The more energy the alpha particle has, the more distance it can go, right? Makes sense? Throw a tennis ball a little, it goes a little. Throw it really hard, it goes farther. It's not quite what's happening, but close enough, good enough analogy. Okay, so here we are. We have an alpha particle at where the heck was it? At 5.307, so way over here. And it can, oops, not full. Here, somewhere up here we have an alpha particle, and it can go a pretty good distance. The reason I said that, and the reason this is important, and the reason I'm pausing everything to state this, is because the Geiger counter is 1 centimeter's distance from the source. So we lose 25%, give or take, of our alphas just to the air. That has to be factored in. If you were testing and calibrating with a gamma source, that wouldn't matter at such short distances as a centimeter. Well, I mean, it would matter, but it wouldn't really matter very much. With betas, it might matter the tiniest bit, but not much. Not at a centimeter. I mean, it would, but not much, not really. Okay, so let's begin. Let me get out my marker. That was just some extra superfluous stuff. You don't need to know it, but you do now. Okay. Alright, so the activity of polonium-210 is equal to 3,700 becquerels. Let us rephrase the activity of my sample. And this is 0.1 microcurie, naturally. That makes sense. Okay, so there it is. 3,700 becquerels. Okay. The energy, that calculation's done. Remember the calculation we were doing? Oh my god, in 10 minutes it did 169,700. Oh my god, that's a huge amount. Let me pull the Geiger counter off. Well, we'll look at that in a minute. First, let's finish this. Okay. The energy that we're releasing is an alpha particle, and its energy is 5 points. I'll move my big old shaggy head out of the way in a second for you to see. Its energy is equal to 5.307 million electron volts. Each one of these has a lot of electron volts. Bam, that's a lot of energy, and that's how many of them. This times that is how many electron volts you get per second. That's pretty simple, right? Rate times energy times time. In this case it's 1 second, so it doesn't need to be multiplied by anything. That's pretty simple stuff. Okay, let's figure out how many joules this is. Joules are an important unit, and they're a unit that we're going to be using for figuring out grays. And once we know grays, we can figure out sieverts. Alright. Alrighty. We're going to do a whole calculation, and then we're going to divide all of it by 2, because we're only getting half of it. Remember I told you that little thing about half, so we'll do that at the very end. 3,700. Foolish me. What am I doing? I'm looking down here at my paper. How did I do this last night? 5.307 million electron volts. And then we're going to multiply that by the conversion factor to joules. 1 million electron volts to joules is equal to this. Well, it's equal to, it's a little x here for times. I'm going to use an x for times. I know it's like bad in football, but I'm going to do it anyway. 1.602176 times 10 to the negative 13 joules. Alright, let's figure out what I just said here. I know that every million electron volts, every 1 million electron volts equals that many joules. It equals 1.602176 times 10 to the negative 13 joules. That's how much right there is in 1 million electron volts, and I have 5 of them. So it's going to come out to like 6 or something, maybe 8, maybe, yeah, 8. it equals every single alpha particle coming from that polonium produces 8.503 times 10 to the negative 13 power joules. We're getting there. We're getting there. So, this is how much comes out of the polonium-210. That's how much energy, how much go juice it has. Alright? So we know that that's the go juice, the energy of the alpha, multiplied by the number of joules that one finds in 1 million electron volts. You know, we have that number right there. This is the number of joules that are coming out. And if we were to take this number of joules and multiply it by this number of becquerels, then we'd know exactly how many joules we had coming out per second, wouldn't we? It gets so much creepier. Now, let's do the math. Let's do it. Alright. Let me get down low here so I can keep writing. Getting down low, we would like to write our energy. And let's see here. Our energy in joules multiplied by our, well, let's draw it differently, by our activity in becquerels. That is a J, by the way. It looks stupid, but it's a J. Energy in joules times our activity in becquerels. Now, we're looking for microsieverts per hour, right? Everybody does microsieverts per hour. Well, there's 60 seconds in a minute, 60 minutes in an hour. 60 times 60 is 3,600. So the 3,600 seconds in 1 hour. These two dudes here are doing it in seconds, so let's keep it in seconds. This is 1 hour. That's all it is. 3,600 seconds is 1 hour. Okay. Multiplied by our weighting factor for alpha, and multiplied by the weighting factor for what it's doing for the human being itself. Right? Now, we'll do one other thing in just a minute. The weighting factor for alpha was 20, right? 20 times the punch. Right? 20 times the punch. Crazy stuff. 20. And for a human being, it's 1. Oh my god, a 1. Why? Because I'm going to do my whole body. I'm not being specific to my hand. The reality is, the polonium can't affect my whole body. I would have to like rub it all over my body to do that, you know. So, I should be doing it for like my finger or something, but I'm not. I'm just going to do it for the body. And anything in the whole entire world multiplied by 1 is equal to itself. So, it's gone. Now, wait a minute, hold on. What about this? The space. Tom, you just said that you lose 25%, give or take, to that 1 centimeter. It's true. In fact, you lose change in energy with respect to x for 1 centimeter comes out to 25.19%. So, take 100 units, remove 25.19 units from them, and you get the remainder. That means 74.81% does get to you. So let's figure out this. Times 0.74%, 74.81%. This is the amount that gets to you. It's a percentage that gets to you. It's the weighting factor for radiation. That's 3,600 seconds in a minute. So, energy times the activity times the whole period of time you want to do it, multiplied by the amount of damage it does, times the percentage that actually gets to you after being lost to 1 centimeter. I know I'm redoing things and going back, but I want you to understand what I'm doing. if you were doing a beta source or a gamma source, this would be a 1. This would also disappear, and you'd probably end up with something like this. In reality, these are here, plus there should be extra variables too, but with the plus and minus of as much as 10% in accuracy on a Geiger counter, and the fact that all the scaling and stuff doesn't work right on them, then it really doesn't matter. This isn't too accurate. Remember, a Geiger counter should only be doing counts per minute, counts per second. If you're doing Microsieverts, you're wrong. If you want to calculate for it, that's fine. But don't expect it to be exactly accurate. It's not going to be exactly accurate. And if you don't believe me, ask a physicist about doing this. They will first vomit. Then they will explain not to do it. Okay, so but anyway, we're going to do it because we're crazy. Let's do the math here. Thank God I've already done the math, so I don't have to actually do it again. Alright, had a boo-boo, pause the video, math boo-boo. Here I am back now after my math boo-boo. So if I was like in a position and all of a sudden instantly I was in another position, it's because I had a math boo-boo and I cut myself off. Almost forgot. Out there. Here. Divide the activity in half. Why? Because remember I told you I'm only going to be getting half of it. Only half of the polonium can get to me. If it were farther away than it is, then I would have to start taking into account 4-pi geometry, how it expands as a bubble and all this other stuff. But we're close enough that we can ballpark it and say it's half. It might be more like 45%, but whatever, we'll call it half. So half the activity, half of 3,700, that's 1850. If you do this math here, that's 5.503 times 10 to the negative 13th joules, multiplied by 3,700 divided by 2, which is 1850, multiplied by 3,600, multiplied by the weighting factor of 20, multiplied by this right here, which is the amount that's actually getting to you, you're going to come together with a grand total of a smudge that you can't read. 8.473 times 10 to the negative 5 joules per kilogram. Where did the kilogram come from? I just added it. Why? Because we're trying to figure out mass here, and you have to have a degree of freedom of mass. So we're going to put in 1 kilogram, the base of all those little mass things, using SI units. To convert this to microsieverts per hour, where's my better marker for that? Microsieverts per hour are millionths of a sievert. That's pretty close to a millionth right there, right? It's getting there. The answer is 84.73 microsieverts per hour. Bam! There you go. Is my math right? Who knows? We'll find out later when I get my comments back from everybody telling me it's wrong and bad and I did everything wrong. But that should be about accurate. Now we know that that tiny little polonium sample that I have should be putting out this many microsieverts per hour. Let's calibrate the Geiger counter so it reads that. And by the way, let's get back to that efficiency experiment and see how efficient my Geiger counter was. It doesn't matter for this because we know this. If I knew my efficiency but I didn't know this, then I could still figure it out. So if I know one or the other, I'm good to go. Boom. By the way, knowing the efficiency is how you figure out stuff like light salt, for example. So, there you go. Let's figure out how that experiment's going. Alrighty, let's move the camera over here to my other board and see what we get. With my Geiger counter here, I detected 169,700 counts in 10 minutes. Let's wipe what I have here on the board out. I was calculating the radioactive activity of potassium-40 and trying to figure that one out. Let's get rid of that. Doesn't matter. This is my bad board. It has something sloppy on it and I still can't get off whatever's on it. Okay. 169,700 is how many counts I got in 10 minutes. What we're figuring out here is the efficiency of the Geiger counter at detecting polonium-210. And it's fine if it's not 100% efficient, but we'll see what we get here, okay? Now, let's see here. We should divide this first by 10. We get rid of one of the zeros. Now, it is 16,900 counts per minute. Okay? Now, let's divide that by 60 to get counts per second. Let me get my Geiger counter. Why do I always call a calculator a Geiger counter? Wow, that's really strange, isn't it? 16970 divided by 60. And just in case you didn't pick up on that, let me show you again. The Geiger counter says, and it's an overflow mode. Okay, you see if you can see that. It is in an overflow mode. It is at 169.7 times 1,000. It got too big for the numbers to read without going into overflow of times 1,000. So that is 169,700. That was in 10 minutes. We divided it by 10 and we came up with 16,970. All right? Because we don't want to work, we use the 10 minutes so we could become accurate. We divide by 10 to get the average. Okay? Divide by 60 to get the number of counts per second. And enter. That's 282.833 continuous counts per second. The polonium is 282.833. That's pretty good. So let's do this now. Let's figure out how sensitive my unit is. Alright folks, now for some efficiency calculations. Let's see here. The efficiency of the Geiger counter here, and by the way you can see it's cranking. The efficiency of the Geiger counter should be equal to the counts per second I detect divided by the activity. Our activity is a little bit of a weird thing. I just want you to remember. Our activity is 3,700 becquerels, 3,700 decays per second, but we divide that by 2, which gives us 1850 becquerels. And the reason is because we're only getting half of the dose here. Well, not the dose, half of the exposure of the rays are coming out. Only half are hitting us. So 37 divided by 2 is 1850. Let me see if I can show you up here on the board, because I have all the math here. Let me walk over here to the board and let me show you on the board. Okay, so I did a 10-minute count, and in 10 minutes I found out that I was getting 282.833 counts per second. That's all the counts I got in 10 minutes divided by 10. That gave me minutes. Then all the counts I got in a minute divided by 60, that gave me seconds. So 282.833 counts per second is what I ended up with. This is not right, because this is 3,700, the activity, but I have divided it in 2 to make 1850, but that's not really right. And the reason is because remember this bit down here, the 0.74881? I'm only getting 74%, give or take. And to make that work out mathematically, I will need to multiply 1850 by 0.7481. That gives me 1383.3 985. That's the decay. That's the activity that I'm actually going to be looking at because I'm a little bit of a distance away. So with this activity, and I got this many, so this into this gives me that, and that's going to give me this divided by that, the straight up division. Big old point. This is the United States of America, big old point. And those commas. And if you're in Europe, sorry. That's a side question. Why do the Europeans use commas instead of decimals if it's called the decimal system? Unless I'm just ignorant and they don't call it the decimal system. But I'm sure they do. I've been to Europe a bunch of times. You'd think I would have picked up on this by now, right? Well, anyway, so forgetting that. We think our Geiger counter is 20.43% efficient. Now, let's test and see if that's true. Alright, let's see here. Let's see if that is true. Cut on my Geiger counter here. Okay, I did, just a minute ago, in preparation for this, I did a 1-minute test on my Geiger counter, and I got in 1 minute 268.16 counts per second. Now, if I think that this is the right efficiency and I want to know what I really am supposed to have gotten at 1 centimeter, knowing of course already that little bit right there, the 74%, I would already have to know that. And that's okay, because remember that when I think I said this in my video a couple of weeks ago, that when you're trying to calculate all these sorts of things, you need to know your geometries, your distances from things. They're very important. We've done a little bit of ballparking this day, and I hope that it's not going to offend anybody. But 20%, 20.43% is 0.2043. There's a little point here. There's a little point here. Okay. What does that come out to? The answer to that should be pretty close to that. And let's see here. Let's see here. Let me key this in the calculator. Alrighty here. 268.16 divided by 0.2043. And look at that. The answer is 131257. 131257. That's pretty damn close, don't you think? So I think we can call this one true. I think we can say at 1 centimeter's distance. At 1 centimeter's distance in normal standard room temperature air at sea level, my Geiger counter has a 20.43% efficiency at calculating the counts per minute from polonium-210. Now, let's calibrate ourselves. We believe that this is true. The only thing on this that I'm not sure is 100% true is this little conversion right here. I ballparked that off of an integration operation. So it could be a little off, and if I'm off there, I'm sure somebody's going to leave me a nasty gram. But remember what I said, my little disclosure at the beginning of this. This is not standard practice, and it's the reason that you should actually go buy yourself a scintillator. You don't have to do this. Scintillator just tells you this. We think that I should be getting 84.73 microsieverts per hour from my sample. Let's go test. You go over here to the Geiger counter. Geiger counter says 52 point whatever microsieverts. That's what it thinks. Let's change it so it's correct. Cut it off. Press the plus button right here. While holding the plus button, while holding it, cut the thing back on. Let's cut the volume off though, good God. Alright, so we're in the menu. It's going nuts over the polonium. Set to option 7. Option 7, not 8. 7 is the calibration factor. This is a coefficient multiplied by what this thing is normally detecting. Alright? So it's not going to mess up the factory calibration. You can reset it immediately. If you go to option 3 and hit the set button here, it'll go BAM right back to 100%. Every Geiger counter is calibrated differently. Like this guy right here, same type of thing as this one. It has the same basic thing, option 7 and so on. If you have an old CDV 700, you're going to be going at it with a screwdriver. They're all a little bit different. Anyway, we hit the set button, so we go into option 7. And we're going to calibrate this thing. I think I know where to go with this, because I already tried it earlier. 169 should be the right cal setting. Boom, boom, boom. I think that 169 is correct. Press the set button, let it go. Microsieverts per hour. Give it a second, and we're hoping for 84.73. Now it's going to go all over the place because this is a nasty little sample. So it's never going to sit right at something. It's scaling too fast. But as you can see, I'm pretty close. Maybe a little high. 84.73. I'm pretty close. Moves up and down a little bit. Maybe a point or two off would have been more accurate. But the point I'm trying to make here is now we should be calibrated at polonium 210. So when I take my Geiger counter, my trusty Geiger counter, and let this drop down to normal. Let's turn the volume up so you can hear. And I should point out something, that this calibration scaler here changes the entire calibration all over the place for normal everything. For example, if I were to switch this to counts per second, or sorry, counts per minute, I should be getting about 40, but I'm probably getting more like 80. So this makes everything else inaccurate except polonium. You must already know your background and how to remove it and how much it is. Okay? All of that gets messed up. So this is not something you want to run around with. You want to be normally at factory calibration, which is setting 100. I'll show you how to get back. As you approach the polonium, the microsieverts go up, and this is probably accurate. And if I move the pencils out of the way here, and I jack this up a little bit at an angle so you can see it, and I'm going to get this very, very close to this without touching it. I mean, as close as I possibly can get it without touching it. Let's cut the sound off. Absolutely as close as I can possibly get without touching it. That's how many microsieverts per hour my source is. And I think that this is correct. Wow, 116. That's pretty heavy. See, I'll get that back down there again. It's hard to get it close without touching it. It's really difficult to get it close without touching it. Not actually touching it. Close. Impress your friends. You can actually tell them. Now, hold on a second. This is the most important part of the whole video. Here we are in this crazy crackpot polonium 210 mode, and all of a sudden we want to make sure we can test what's the real radiation in the room here. How many counts per minute? Because if you watch this, if we cut this off, go back to menu, switch it to 2, not 2, yeah, 2, and then we switch ourselves back to counts per minute. Notice our calibration factor is displayed at 169. We're still at the wrong counts per minute. So we're going to scan pretty high. We should be getting about 30 to 40, somewhere in there. We're going to be scanning pretty high here, and the reason is because counts per minute are well off because of the calibration factor. If we want to go back to normal, let me show you how to do that rapidly. Cut the unit off, press the set button, set the plus button, cut it back on, go in the menu, go to menu option 3, hit the set button. Bam, back to 100% calibration immediately. There you go. Give it a minute to become accurate. So that, folks, is how you calibrate for a source. Polonium is probably the worst source on Earth to calibrate for because, well, it's so moody and crazy and all over the place. The math is very difficult too. It's much easier with with gamma and beta sources. But I'm fresh out, so this is what you get. Alright, so what have we learned today? This Geiger counter, an inspector plus, radiation alert inspector plus EXP, is, in the regular one should be the same, is 20.43% efficient at calculating polonium-210 at 1 centimeter's distance, and at 1 centimeter's distance on a calibration setting of anywhere from about 165 to 169, it is accurate in displaying 84.73 microsieverts per hour. You can use this math and this way to calculate for other things too, but you have to know what the energy amounts are, and sometimes that can be quite tricky. And remember, kids, don't try this at home. Oh, and if I got the math wrong and anybody sees math errors, because I do that sometimes, please tell me. Anyway, this has been Tom from anti-proton.com. Have fun.